are we close to general artificial intelligence? Hard question. First of all, what is that? Some people argue autonomous learning is an important aspect of it. Human-like cognitive ability is something that comes up a lot. Consciousness, self-awareness, sounds even science fiction-y. But I'll focus more on the generalization and the versatility and adaptability. Especially the latter one. I think it's arguably an important thing for if you want to talk about the general artificial intelligence. So you want a model that can handle any kind of thing in various ways, maybe. Okay, so point is we need versatile models to solve different learning tasks or to combine different learning tasks. So let me make it more specific. If we have this data set here, these are these are measurements of some water property at 7 different locations, and these are sensors. So at any point, like it doesn't work on the screen. So you see where the orange parts are. At some point, there is data missing. So if we would have to remove all of this data, you have a problem. So what do people do? We do a data imputation method, and then we solve the learning task. But okay, what if we can combine it with a model that does it all? That would be interesting. Okay, so that's exactly what we will propose with a kernel principal component analysis setting. And we'll talk today about the versatility of this framework. So it's more like a general overview of different works and also ongoing work. So we start from some super objective term. And what is it? It's basically you have this energy function which you want to minimize subject to some regularization. So we have the green energy function, and we regularize some primal variables u or some dual variables h. So we have this duality like in kernel machines, and we have additional regularization on the learned representation. So that's the loss in a nutshell. But the point is there's a primal and a dual aspect in this model. Okay, so we have the super objective. In previous work, we showed a lot of equivalences because we can solve on the left towards the primal optimization to the primal variables, or on the right the dual variables, and we all have these equivalences between them. We can use eigendecomposition based models like really in the well-known PCA problem, or we can take constraint optimization approaches just to arrive at the same solutions. So point here is we have like a spectrum of 4 algorithms which we can use all to solve the same problem in some different way. So that would definitely add to the versatility of kernel principal component analysis. Okay, so depending on the task, we use one of these 4 algorithms. And this is the kernel PCA framework. Like it's in a multi-view framework. Let's break it down. Let's say you have some representation here, and you want to project it, like in a PCA setting, to a new representation here. That's just this. So this you can see as PCA. If you have 2 data sources, then you can combine them, project them to the same space. And if you want to have a more powerful model, you can learn some representation of your input data first. Okay, you can also project back in some cases. So that's on the left in the primal setting. In a dual setting, you do equivalent things, but with kernel matrices, so comparisons between data points, and you add the different modalities of the data, and then you solve for it. And this E and H are the primal and dual representations respectively, and they really have the same information. It's even just a scalar relationship between the two. Okay, so that's a lot to digest, but I'll make it more specific now. So let's say we want to do a supervised learning task. I'm just talking about PCA, it's unsupervised. But what if we just say, okay, the first view is some data, and the second view is the label we want to predict. If we then say, okay, we solve the PCA problem, the multi-view PCA problem, so we have this U matrices, but we also want to learn in the meantime some parametric mapping, like a convolutional neural network, for example, in this case. And if we combine this, we can reconstruct the label. So That's the unsupervised terminology to say, okay, we predict the label. So in practice, you can do supervised learning tasks within the setting. Okay, what's next? Data imputation. So now in the dual framework, for example, we use a kernel function. So just to compare different images with each other. And just by solving the PCA objective, which is now formulated in some backpropagation formulation and some the dual variables. But the point here is we just solve the kernel PCA problem, so we look for this H representations, but we just add parts of the data, like the data that is missing, as optimization parameters. And by solving for this, you see that, okay, this ground truth 8 is quite nicely reconstructed, considering you don't really solve a data imputation objective or anything, you just solve the PCA problem. Okay. Now other work from the past is like, okay, we can do generative modeling as well. So now I reduced the figure a lot. So we see here we only have one view in this particular example. We want to learn a feature map, which is again a convolutional neural network. The PCA representations, projections to have some latent representations, as in the blue, space there. And if you project back and you run an inverse mapping, you can just sample from the latent space and generate new data points. So all within this kernel PCA setting, we have supervised learning, data imputation, generative modeling. We can solve it with primal and dual. So we can tackle different learning tasks, and we can use actually cast very powerful neural networks as a feature map in this framework. Okay, so this super objective and the kernel principal component analysis framework, they are it is very versatile. You have different algorithms, many learning tasks. So what are the limits? And ongoing work now is like, okay, can we combine these things? I mean, if it can do anything, can we, and to what extent can we combine these things? So this data specifically came from Vito with the question, okay, how can we efficiently do some regression task with this data? Well, there's many missing data. So that's ongoing work. So to conclude, are we close to general artificial intelligence? Well, most likely not, but we do have some nice generalization ID in this unsupervised framework to solve many problems. And I hope I brought the point home that it's a very versatile and adaptable framework.